Okay, what we'll do in this podcast is we're just going to do a Unit 1 review, talk about the stuff that we should already know this. So this is just going to be quickly, 10-15 minutes. If there's anything you don't know, that is the stuff you ask questions on, or you come back and get some more work on. So we talked about matter, we talked about measurement, unit conversion, which is probably the big thing that we need practice on, significant figures, and scientific notation. I'm going to add one thing into here, is a small discussion on accuracy. On accuracy and precision. So just one little discussion that we didn't include in the other podcast that we really should be talking about when we're talking about measurement, because they go together. Okay, so first we talked about matter. This one's a little bit small, but everything is matter, right? It takes up space, it has mass. It has volume and mass. It is matter. It doesn't matter. Our matter is broken down into either pure substances, with either can be elements or compounds. Make sure we do have a decent definition of what an element is, and a compound, which again is a set ratio of those elements. On the other side, if it is not an element or a compound, it's a mixture. Mixtures can either be homogeneous, which means they appear uniform, which mostly are solutions. Most solutions are homogeneous. Milk, coffee, etc. Soda pop. Heterogeneous means they look like they're different. You can tell that they are not, they're not the same stuff. And notice this as particles get bigger, which is true. The other thing we need to know, there's a few things we need to know, is that our mixtures can be separated into pure substances by physical processes, correct? So we don't need chemical reactions. We can filter, we can evaporate physical processes to take mixtures into pure substances, and we can move compounds into elements. We can separate them via chemical processes. So this is where we have chemical reactions, is taking our compounds and breaking them into elements. Mixtures can be separated into pure substances via physical means, and elements cannot be broken down, cannot be further decomposed, well, except for if we have some nuclear decay type of reactions, but we won't go there right now. The other piece we want to know about matter is that matter, the state that matter is in, we want to know about the states of matter. Again, all you have to know is about the three states of matter, liquid, solid, and gas, but we do want to know its relation to energy, that gas molecules are moving faster, and they have more energy than solid particles. So solid particles, again, they're still moving, they're vibrating about a fixed position. In liquids, they're smooth, they're spread further apart, and in gas, again, they have no volume and no shape, right? Whereas liquids they have a volume, but no shape, and our solids have both a shape and a volume. Okay. And we won't talk about anything, we're not really going to get into plasmas or non-Newtonian fluids or anything crazy, just our three basic states of matter. We need to know how to measure our matter, which is where our international system of units comes in, our Scientific International. Again, we have base units, we have derived units from those. We have more units than are even listed here. We have things like density and such that we'll use. This is just a summary of some important ones that we use in science, and we also have our SI prefixes. And again, our prefixes can go with any of our base units, any of our derived units, and they just tell us how big or small they are. So we could have, for instance, picovolts, or picocoulombs, or picowatts, or picojoules, or picomoles. Oh, I like picomoles, or picoamps, picoseconds. So again, any of our prefixes can go with any of our base units, and these are the values that they are. So 1 tera is 10 to the 12th, a giga is a billion, a mega is a million, and it's a million of whatever we're looking at. So a megasecond would be a million seconds. After we measure and we get units, somebody was using their yardstick and they measured something in inches. Well, we want to be able to convert those into other units. And so we use a process called unit conversion, or sometimes it's called dimensional analysis. So what we use is we use our starting amount. We take what's called a conversion factor to multiply it by. In this case, we're converting feet to inches. So inches goes on the bottom. There's 12 inches in 1 foot. So 12 inches go on the bottom. We cancel those out. We get feet. But again, we won't be using English units very often. More often, we'll want to maybe take those English units and convert them into metric units. So notice we can convert the top. We can also convert the bottom. Here's an example where it says the space shuttle travels at 17,000 miles per hour. How fast is that in meters per second? Well, we have miles over hours. Notice our next conversion factor is converting miles to kilometers. Notice miles is on the bottom, so it cancels. Then kilometers to meters, where kilometers is on the bottom. 1 kilometer is 1,000 meters. That cancels. Now we have our right units on top, which is meters. Then we just convert our hours. 1 hour is 60 minutes. Notice this time hours goes on top because it's on the bottom over here. That's the unit we're trying to cancel. Now we have it in minutes, and 1 minute is 60 seconds. Again, minutes on top, seconds on the bottom, because we want it in meters per second or meters over seconds. So we just line up our units so they come out the way we want them. And then you pick up your calculator and you do the math. Lots of these, right? We don't need to go over all of these. Hopefully you've done enough practice. We also had significant figures. So we have some significant figure rules. Remember, all non-zero numbers are significant. Any zeros that are sandwiched are significant. Zeros to the left are not significant, so it all depends on the trailing zeros, whether or not these are significant. Notice, like it says, they're significant if they follow both a decimal and a non-zero number. So these zeros are not significant because they just follow a decimal. The ones back here follow both the decimal and a digit, a non-zero number, so they are significant. Last one, again, zeros to the right are not significant unless there's that decimal point. We need to have that decimal point. Notice there's 2 significant figures. It could be up to 6 if there's a decimal. Sometimes they'll make a line over the top to indicate that unit has been measured. Okay, so quick rules for significant figures. Then on to our scientific notation. Hopefully we can convert into and out of scientific notation. So notice if we have a really big number, we'll move that decimal 1, 2, 3, 4 places. So it's 10 to the 4th. If we have a small number, we'll move it in the opposite direction, 1, 2, 3. Again, beyond the first non-zero number. Now we move it the backwards direction, we get a negative exponent, right? We also need to make sure we know how to measure things correctly. And remember, we have kind of 2 different systems. We have analog scales, which means it doesn't tell you the value, you have to read the value. And we always need to estimate one place beyond the scale that they give us, and then the error that we report is half that smallest gradient of the scale. So it changes with whatever tool. So if I read this one, again, I'm reading it from the meniscus, and these are a little bit blurry, but that is 20. This is 25. So this volume I have to read from the bottom of the meniscus. So it's 1, 2, 3. Ooh, it looks like it's just about on, maybe just a little bit above that 3 marker. So it is 23. I'll estimate that last place, 23.2. Again, that's what this rule is saying. Estimate one place beyond the scale. The scale goes to the one place. I estimate to the 10th. Now my error is half the smallest gradient, or half the smallest place that you can measure to. So again, we go up every one, 21, 22, 23, 24, 25. So half of 1 is 0.5 milliliters. So accurately measured, this would be 23.2 plus or minus 0.5. And so if you estimated this differently at 23.1 or 23.4, that is why we have that error. Okay, that's an analog scale. That works for all analog scales. Next one. Now we have a digital scale, and again, digital scales are a little bit easier. We'll put our dish on the scale. We'll hit the tare button, or this one that's called a 0 button. On some of ours it's called tare. Other times it's 0. So we put that dish on. We 0 it. We put in what we want. This looks like some copper sulfate probably. And then we'll read off our mass, 54.05. So we'll read all the digits they give us. We won't drop them off. And then our error on this value is going to be the smallest place that they give us. So 0.01 grams are our unit. So again, we need to make sure we read all the values they give us on our digital scales. Last bit we need to talk about that we haven't yet is the difference between accuracy and precision. Ooh, and this gets a little bit confusing, but this is a beautiful graph to remind us of what these things mean. Okay, so first, if I look at precision, what precision means is that your results in lab are reproducible. Your results are good. So you get the same result over and over and over again. So your results are reproducible. That means they are precise. So notice, precise, they're all clumped together right here. Precise, they're all clumped together right there. Now, just because, oops, we'll bring that image back here, sorry. So just because they're clumped together does not mean they are accurate. They are precise because they're reproducible and you're getting the same value every time or close to it. Accuracy is how close you are to the actual. So notice, in this one, they are very accurate and they're very precise because they're reproducible. You're getting the same value over and over again, and they're right on the bullseye. They're right on the number we want. Notice, these are imprecise there's a lot of reproducible error, or sometimes this is called random error. So there's a lot of random error. Notice, but the average of these is very accurate. If we average those together, we could still get an accurate value. Notice, sometimes we'll have very precise values that are reproducible. We get the same thing over and over and over again, but they are not accurate. They are inaccurate. That is sometimes called a systemic error. So there is something wrong with our process, is what systemic means. That's systemic error. There's something wrong with our process, which is why we are getting inaccurate but precise errors. Last scenario is we could have both inaccurate and imprecise data. So the data has a big spread and is nowhere near what we want it to be. Obviously, that is what we're trying to stay away from. What we want, obviously, is accurate and precise error. But what we want to know right now is really the meaning of those terms and how the error generates those. And we'll talk more about how the error generates either accurate or precise data as we go forward.